In this video, I wanted to define what is the difference quotient and talk about how that relates to functions and finding the slope of the tangent line. So basically, in the last video, I talked about average rate of change, what that means, and I explored what happens if we apply change in variables. But the difference quotient is what we define to be this mathematical function. It's the difference between f of x plus h and f of x all divided by h. But what I wanted you to notice is really it's the same formula as the average rate of change formula, but instead if we use a is equal to x and b is equal to x plus h, what happens is we have x plus h minus x, which leaves us with just h in the denominator, just as we did down here. And then in the top, what we're left with is f of x plus h minus f of x, which will often have a cancellation of many common terms. And what that leaves us with is an algebraic expression, which gives us a generic slope for the equation at any point in time. Because notice in this example, we found the slope of the line. It wasn't at specific examples, it was by using a very specific approach. And it's an algebraic strategy for progressing through the average rate of change without knowing what a and b actually are. But basically, if we make that substitution, b is x plus h, a is x, what we're left with is f of x plus h minus f of x over h. And basically, this is sort of like checking the difference between x and x plus h between 2 points. And as long as we divide it all by the difference between them, we're going to come up with an alternative formula for the slope of a secant line. But the last little bit here is, well, this would give us the slope of the secant line between x and x plus h on a curve. Or basically, this would not give us the exact slope, this would give us an average slope. As I described before, when I find the average rate of change, it's giving us the slope between 2 points, but not the slope. It's not exactly the slope of the curve, but it's kind of an approximated version. But what I wanted you to also see is how can we improve the slope and what's the idea behind that. But in a demo that's kind of relating a secant line to a tangent line, remember that a secant line is the average slope between 2 points. Basically, it's a line connecting 2 points on a function. But notice that actually, if I bring the 2 points closer and closer together, this is kind of the key idea in calculus, what will happen is the secant line becomes closer and closer to the slope of the line itself. Like, right, notice if I move it further apart, that secant line is less accurate at determining the slope of the parabola in between the points, right? It's an average. It's not exactly perfect calculation of the slope. But if I bring them closer and closer together, notice that that line gets closer and closer to the curve itself. And actually, if I bring those points exactly together, what I end up with is no longer a secant line, but a tangent line. Basically, if those points merge together, what I end up getting is the tangent line for the particular point. But this is the main problem with a tangent line on the algebraic side, is that if I try to use that, like basically, notice that on the tangent line, both b and a, both the points are the same. So let's say b and a, they're both equal to 1. The issue, mathematically speaking, is if I try to use b and a, if they're both 1, what I get is there's no rise and run. I can't find the slope of those points because what I get is 1 minus 1 in the denominator, which is 0. Or if I think about this in terms of x and h, we defined x to be the first point and h to be the distance between them. Basically, the idea here is we're looking at what will happen as the points get closer and closer together, which is an idea for bringing what will happen as h gets closer and closer to 0. Because h is just the distance between those 2 points. And if I get them closer and closer together, basically h is getting smaller and smaller and smaller and smaller. And we'd like to get it all the way to the point where literally they are not apart, h is 0. But again, the issue with h being 0 is this is not defined. In math, we can't divide by 0, so we run into a dead end on the algebraic side. But essentially, there's a little trick behind this, is that if we start with the difference quotient, simplify it, and then apply what we refer to as the limit as h approaches 0, it's a way of dealing with the nature of having an undefined value within the difference quotient. And basically, let's look at an example of doing this by returning to the same linear function we just did. What you can do, this is something which I would ask you to do, is simplify the difference quotient, which all that's meaning is that take this algebraic expression, apply it to the function, and use algebra to simplify. But basically, what I would always start with is that difference quotient, which is f of x plus h. So if I'll just go ahead and write that out. But really, the thing that's important here is that the difference quotient is the same as the average rate of change. It's just it's expressed a little differently, and the goal is to help us to simplify it using cancellation of common x terms. So if I apply that f of x plus h, well, we already solved that, which was 2x plus 2h minus 7, minus f of x, basically subtract the original function and divide it all by h. It's kind of a good starting point for finding the slope. And then if I do the algebra, which we already did in the last video, that would leave me with 2h over h, which is 2. And the difference quotient will give me the slope of the line at any point if I simplify it properly. In that example, the h actually canceled itself out, but that is very unusual. Usually the difference quotient is not just a number. It's actually usually a mathematical expression involving x and h together. So let's do a fresh example, and we'll talk about like how that works in a more complicated example. So with g, again, we would start with the difference quotient expression, which is going to be g of x plus h minus g of x all over h. And again, we can change f to whatever our function label is, which does not matter. And then my goal now is to figure out, okay, what is all this, and simplify it. But the key thing here is that, well, the thing that we don't know is, well, what is g of x plus h? We know g of x is that. We know h, just an h. But g of x plus h is something we want to consider. And another thing to be very careful about is, remember, if g of x plus h is not just x squared plus 4 plus h, because here the x plus h is in the input. So if I was to figure this out, I need to plug it in for all the x's, right? Because if I'm going to do g of 2, that whole thing would need to go into the x. So g of x plus h, and we talked about this way back in chapter 2 at the beginning of the semester, but it's good to review because this is important in calculus. But this would give us well, normally g of x is x squared plus 4. So here I'm plugging in x plus h. So x plus h would need to be inserted in to the square plus 4. So that would leave us with this. And to do this, I would need to properly FOIL this all out. So that would be x squared plus 2xh plus h squared plus 4. Because really this means x plus h times x plus h, which is not just x squared plus h squared. Just to review. So anyways, g of x plus h is all of this stuff. And if I plug that in for right there, that would be x squared plus 2xh plus h squared plus 4. All of that is my g of x plus h. And I notice that I'm using parentheses, which is always my recommendation when simplifying the difference quotient. But this would then be minus g of x, which is just my original function. And I want to make sure that I'm subtracting the whole function g of x. So I'm going to use parentheses, and that's all divided by h. And then now that's kind of step one, is plug in the functions g of x plus h and g of x and solve, well, what is g of x plus h? Then after I do all of that, then I can actually simplify this algebraic expression. And notice that, well, what I have is x squared minus x squared. Those will cancel. And then I have plus 4 minus 4, because really, it's not 4 plus 4, because the whole thing's being subtracted. And what you'll notice, kind of like in the last example, is there is very typically a cancellation of common terms, which is why this process actually works. And so what happens is we're left with 2xh plus h squared over h is everything we're left. And this is basically what we're left with. And last thing we want to do is simplify and cancel. But one thing to remind you about is be very careful about canceling this, because this is a 2-term divided by 1 term. Really, both terms need to be divided by h. Or another way that you probably remember of how you want to do is you want to make sure that in order to cancel, if you're going to use the cancellation rule, you want to factor it. But notice that h is a common factor in the numerator, so I could factor that out. And then once I do factor that out, now I could cancel. But basically, don't cancel like this. That's an error. That's an algebraic error. I've seen students do that many times. And these are the things to look for as these are mistakes that are made in calculus. So the algebra is a little bit hard, but what we're left with is 2x plus h. And this is the simplified version of the difference quotient, and that's just about it. And so the last little bit here is that we're not quite done, but basically what this is saying is if I'm trying to find the slope of the secant line, I could plug in, well, what is my location and what is h? And this will give me the adjusted slope for this parabola. But additionally speaking, kind of what I was saying in this demo here is that our goal is to view what happens as h goes to 0. And notice that in simplifying the difference quotient here, after I finished simplifying, the h in the denominator actually ended up canceling, which left me with an expression where h could be 0. And the last step for calculus, and since we haven't really, you're going to talk a lot about limits, and it takes a long time to discuss the meaning of limits properly, but the gist of it is that in some context, what happens is we just plug in h is equal to 0, because here h is defined to be 0, and I'm allowed to just figure that out. But basically, we often define, but anyways, that would be the difference quotient. That's the end of that problem. But let's say I wanted to find what is a derivative of a function, and what does that mean? We often refer to that using f prime of x as a notation for what a derivative is, but that's always defined to be the limit as h approaches 0 of the difference quotient of that function. But basically, since I've just solved the difference quotient, in this case it's the limit as h approaches 0 of that expression to which I just figured out algebraically. And basically what it amounts to as, well, what happens as h is 0? Well, that would just be 2x plus 0, which is 2x. And again, we're not getting into limits right now because that's something that you're going to talk a lot about in calculus, but at the end of the day, what we get is what we refer to as a derivative of our original function, which is 2x from the difference quotient. Now, for those of you who've had calc before or who have heard certain rules, there are what are referred to as like what's called the power rule, which is like if you're trying to take the derivative, what you do is you drop the 2 and you subtract 1 from the exponent, which gives you your derivative. But in calculus, you're going to learn all sorts of rules for finding derivatives. Those are all predicated on the original difference quotient, and anytime that you're talking about derivatives, it's always based on this math. So the math is there's a lot of algebra involved, but the sense of it is to find the generic slope of the tangent line, as I did right here, between any 2 points. And we can do that, oops, I didn't mean to do that, by applying this algebraic strategy. So again, this is all too much to do in one class period and in one lecture. But what I wanted to focus on is the algebra, and the end result is the solution to the tangent problem, which gives us the slope at a different point in time. And notice the difference here is the slope of the line was 2, regardless of it. But in a parabola, the slope is dependent on where I'm at. And our implication here is that the slope of this parabola is twice the location. So like say, for example, I'm looking at the slope at this point in time. Let's see if that actually makes sense. But if we're examining the tangent line right here, notice that if I'm at exactly the point 1, what that formula would suggest is that the slope of the line would be 2 times x, 2 times 1, which is 2. And if I'm looking at the slope of this line, notice that if I'm kind of looking at the tangent slope, it's got a rise of 2 and a run of 1. So its slope is 2, exactly what that function tells me. And if I move the location of this point to say over here, say for example, if I move it to point 2, notice that the slope is different because it's a lot steeper, it's further along the curve. And essentially what a derivative function does, what the point of it is to find the slope at each location x. And notice how simple this is. The answer is quite simple, but the math that goes into it is not. Anyways, there's a couple more examples of finding the derivative using the difference quotient here. These ones are a little bit more complicated algebraically speaking, but on the final exam, I will give you one of these problems as extra credit. I won't make them as hard as these ones, but anyways, try these out for yourself and see if you can figure out how to simplify the difference quotient in the following few problems. Anyways, that is it for this semester. I'll be posting an announcement and giving you guys some extra office hour times as we prepare for the final. Anyways, sorry that this week there's been a lot of lecture and it's been quite heavy, but we are running out of time and that's just kind of how it goes sometimes. Anyways, hope you all are well, and I'll see you in Zoom if you have any last questions before the final next week.